Okay, well, welcome to our seminar. Our speaker today is Jeremy Hume, and he will speak about characterization of zero singular ideal in non-Hausdorff et al. Groupoid C-star algebras. Please, Jeremy.
Sure. Okay, thank you, Giselle, and also thank you for the invitation. Yeah, my talk will be on non-Hausdorff et al. Groupoids. So let me just start off with recalling the definitions and notation. Um, in this talk, I'll assume a familiarity with groupoids, um, and the setting is that G is a locally compact et al. Groupoid with Hausdorff unit space. Now, um, the locally compact part also means that the product map and inverse map are continuous. And a tau means that the target maps from G to the unit space are local homeomorphisms. And since we're assuming the unit space is Hausdorff, actually the groupoid is going to be locally Hausdorff, but not necessarily globally Hausdorff. Okay? So we got a locally compact groupoid, which is only locally Hausdorff. Some more notation. We'll call a bisection a subset of U for which the range and source map, uh, when restricted to U, are injective. And we'll denote by curly B the collection of open bisections. And for two subsets of the unit space, X and Y, we'll let G for Y lower X be the collection of groupoid elements for which the range is in Y and the source is in X. And then when we're just talking about a singleton X, we'll denote the the same set just by G upper X lower X, and that's actually a group just by the groupoid operations called the isotropy group at X. So the most basic example of a non-Hausdorff et al. Groupoid is the line with two origins. So that's a standard counterexample in topology. You take two lines and then you glue them everywhere except the origin. And here let's index the two lines by elements of the group Z mod 2Z. So with the quotient topology, the basic open sets are essentially open sets of the line, but you also have to keep track of which origin is in this open set. Yeah, so that's denoted by a little I. And square brackets here just mean equivalence classes. So those are the basic open sets of the topology. And then the range and source map, they send an equivalence class of the form IT to one of 0T. So basically, it's the identity everywhere except the origin. And it maps the open set UI to U0. You give it the groupoid structure coming from essentially a group bundle of Z mod 2Z. So two things are composable if the spatial component is the same, and then you compose them with respect to the index, just like addition in Z mod 2Z. So, and this is how the product works on bisections. So other examples include groupoids of germs of discrete group actions, groupoids associated to transversal dynamics of foliations, and groupoids from pseudogroups. So all these classes of groupoids, they have standard, so some basic examples of groupoids that are non-Hausdorff and et al. Okay, so these are the groupoids, and we want to construct a C-star algebra out of them. So first, we have to define a convolution algebra and then take a completion under some norm. And traditionally, for groupoids, if they're Hausdorff, you can just choose the compactly supported continuous functions. But for non-Hausdorff groupoids, there isn't enough of these functions, so you need to expand your class. So we'll denote that class by curly C. Um, and these functions are defined first from uh, functions that are essentially supported on open bisections. So you take an open bisection and you look at a function, compactly supported continuous function on that open bisection. And remember, the groupoids are locally are the unit space is Hausdorff. So on a bisection, since the range and source are local homeomorphisms, the bisection will be actually a Hausdorff space. So there's lots of compactly supporting continuous functions on a bisection U, and you could take a function there and then extend it to the whole groupoid just by setting it to be zero off of the bisection. So you could regard a function in CC of U as a function on G in this way, and this extension is not necessarily a continuous one, so you can get discontinuous functions in this way. And then curly C is defined to be the span of all such functions regarded as functions on G. And then to define convolutions, this is done in the same way as you would for Hausdorff italic groupoids. And similarly for the involution. And you see that this algebra is closed under convolution and involution just by looking at what it does on these compactly supported continuous functions on bisections. So we have our convolution algebra, and we want to complete it into a C-star algebra. So for each unit, we can define a left regular representation, which is a star homomorphism from curly C into bounded operators on L2 of the source preimage of X. And the way this is defined is you view a vector and then you define using the convolution formula above. Okay. And then you get the norm by taking the supremum over all these left regular representations. And the completion will be our reduced groupoid C-star algebra that we're interested in. So is there any questions about the definition? Okay. So some more examples that are modeled by potentially non-Hausdorff Fatal groupoids are Nekrashevich algebras associated to self-similar actions, as well as semi-group C-star algebras. So unlike their Hausdorff counterpart, non-Hausdorff Fatal groupoids are still poorly understood relatively. So it's not known whether, uh, given some nice regularity property like nuclearity or say like a Haber property, whether the groupoid C-star algebra satisfies the UCT. Um, or there isn't really well, hasn't really been studied, but conditions on the groupoid for which that would give you a purely infinite groupoid C-star algebra, as well as Z stability and things like finite nuclear dimension and structure of traces. So there's lots still unknown about non-Hausdorff et al. Groupoids. So a couple of things that are known just this year, nuclearity of the groupoid C-star algebra was characterized in terms of an amenability property of G. This was first done by Buss and Martinez this year. And then later in this year, me and some co-authors gave a different proof using a different approach. And in 2019, it was characterized when a groupoid C-star algebra is nuclear and simple. So in their paper, amenability of G is actually stated as nuclearity, but if you apply the characterization in 0.5, then It reads like this. The groupoid C-star algebra is nuclear and simple if and only if G is amenable, effective, minimal, and this thing J is 0. So amenability, effective, and minimality are all groupoid properties, except for this J here. J is called the singular ideal, which is all the functions. So an element in the groupoid C-star algebra can be viewed as a function on G, and the singular ideal is the set of all functions in the reduced groupoid C-star algebra for which with a zero set dense in the groupoid. So these functions actually exist, which is kind of surprising given it in the Hausdorff case, all functions in the groupoid C-star algebra are actually continuous. So anything with dense zero set would actually be 0 in that case. But since we have possibly discontinuous functions, up, up to this point, the singular ideal has not been understood in terms of a groupoid property, um, except for in some special cases. So uh, the singular ideal vanishing has been characterized for Nekrashevich algebras of contracting self-similar groups. Um, there's some previous progress on this results, but it was resolved by Gardella, Nekrashevich, Steinberg, and Vodovna this year. And the previous progress was done by Steinberg and Shakic. Um, C-star algebras of groupoids with torsion-free isotropy have a nice characterization of when the singular ideal vanishes. Uh, and this was done by Neshviev and Schwartz. And this year, C-star algebras of groupoids with a certain finite, with a finite non-Hausdorffness were also characterized this year. I won't go too much into what this means, but it's a condition that includes the class of Nekrashevich algebras of contracting self-similar groups. And this was done by Brix, Gonzalez, me, and Chen Li. Yeah, so in my paper, I characterize this in full generality when the singular ideal vanishes in terms of sort of a groupoid property. So for starters, we can always assume that the groupoid is covered by countably many bisections for if we just want to characterize when the singular ideal is 0. And this is why, and the reason why is if you have a non-zero singular ideal, it'll always intersect some groupoid, some C-star algebra of a open subgroupoid, which is covered by countably many bisections. So if you want to go past this case of covered by countably many bisections, you get a characterization, but it's sort of in a local sense. So, but really this is a large class and it includes sigma compact groupoids. So it's fairly satisfactory for most purposes. Um, yeah. So I need to define some things first. So if you have a net of units which converge to a specific unit U, let's say, then you can look at the limit set of this net inside of the groupoid. And that is the collection of all groupoid elements for which this net converges to. And so this is a non-Hausdorff groupoid, so this collection could be bigger than just the unit, right? And actually this is a subgroup of the isotropy group. And the way you see that is just by continuity of the groupoid operations. So if the net converges to G and it converges to H, then take the product, u lambda squared, that converges to g times h, but u lambda is a unit, so u lambda squared is u lambda. So you also get that the net converges to g times h. And similarly with the inverse, so you get a subgroup of the isotropy group. Oh, and the reason why everything is inside the isotropy group is essentially if you just apply the range map or the source map to u lambda converging to g by continuity, that gives you that u lambda converges to the range of g and the source of g. But it also, by assumption, converges to u. And since the unit space is Hausdorff, those limit points have to all be equal. So range of g is equal to u and source of g is equal to u. Is there any questions about that? Okay. So, and we'll say a net of units as above is maximal if every subnet of that net has the same limit set as the whole net. So if you go to a subnet and you look at all its limit points, this is going to be potentially a larger set. But I'm saying that the net is maximal in the sense that you can't build a larger limit set by passing to some subnet. And using a compactness argument, you can always find some subnet of a net which has maximal limit set. And we'll say finally that a unit is Hausdorff if for every net converging to that unit, the limit set of that net is just equal to the unit. So you can't get any more limit points. And let's denote the set of Hausdorff units by C. Now, we want to build a collection of subgroups of the isotropy group. And this is denoted curly X of U. And it's the collection of subgroups which are of the form X, which is a limit set of some maximal net U lambda, which consists entirely of Hausdorff units, and with the net converging to the specific unit U. Yeah, so curly X of U is the collection of limit sets of maximal nets of Hausdorff units. And using the fact that when G is covered by countably many bisections, the Hausdorff units are actually dense in the unit space. And from that fact, this collection of subgroups is always non-empty. And you can see that it's actually a closed set in the Chabaudy topology on the space of subgroups. This is also invariant under conjugation by isotropy elements. So this is actually something that's studied in group theory. It's a starting point of the theory of invariant random subgroups, as well as if you care about the probabilistic aspects, but if you care about the topological aspects, people study uniformly recurrent subgroups, and this is the same setup. So I should say, since these definitions are very important for the talk, is there any questions about them? Or I can move on. Okay. So each of these subgroups determines a unitary representation. It's usually called the left regular representation. So this G should be G. This should be the isotropy group of G. Sorry, this should be G upper U lower U. But the unitary representation is defined on the left cosets of the subgroup X, and it's implemented by coset translation. So the standard basis elements of L2 of the coset space are just the just denoted like this. For each coset, you get basis element, and then the isotropy group, it just translates the standard basis. So that's a unitary representation, and we'll uh, consider the direct sum of all these quasi-regular representations, and we'll denote it like this. So the first theorem I want to mention in my paper is a characterization of when the singular ideal vanishes when the isotropy is immutable. So let G be an Étale groupoid and assume that the isotropy groups are immutable. Then singular ideal vanishes if and only if for every unit, the left regular representation of the isotropy at that unit is weakly contained in the direct sum of all these quasi-regular representations associated to the subgroups that we defined above. Okay. So it's kind of interesting. You have on one hand, you have an ideal which is constructed from functions that are supported on meager sets, and on the other hand, it's a property about the geometric property about the isotropy groups relative to some collection of subgroups that are defined from the topology of the groupoid. And just a reminder what weak containment means. In this case, the left regular representation is weakly contained in this direct sum of representations, if and only if for every finite set F that doesn't include the identity element and epsilon greater than 0, there are vectors psi I in L2 of some of these coset spaces, finitely many vectors, such that the vectors sum up to 1. And if you translate them with the group action and then measure them against their inner products, take the sum, that will be less than or equal to epsilon for all translates G inside of F. Equivalently, it's whether you can approximate the canonical trace on the reduced group C-star algebra of the isotropy using vector states coming from these L2 spaces. So I'm going to move on if there's no questions. Okay, and then the general case is very, very similar. So without assuming amenability of the isotropy, it's just that this weak containment property gets relaxed a little bit. So I won't state the definition because it's very similar to weak containment above. But what changes uh, is essentially you allow yourself to choose vectors inside sort of tubular neighborhoods of the isotropy. Um, and you have the same conditions. And then, well, if you want to translate these vectors by the group elements, and these vectors are not in the isotropy, then you have to define what you mean by a translate of the group element. And you do this using bisections. So you fix bisections, open bisections around the isotropy, and then you can just define this translation via convolution with the indicator function of the bisection. So yeah, it's very similar. And I should remark that this definition is not dependent on the bisections, and it's only weakly dependent on the groupoid. So if you have two groupoids that have sort of local groupoids around the isotropy, local open subgroupoids around the isotropy that are isomorphic, then uh, weak containment relative to one groupoid is equivalent to weak containment of the other groupoid. So yeah, so theorem B is that let G be an étale groupoid, then the singular ideal vanishes in general if and only if the left regular representation at the isotropy is G weakly contained in this direct sum of representations for all units. Is there any questions about that? Okay. Um, so I'll start talking a bit about some of the ingredients and how to prove this. So the main strategy is to reduce the problem to problem about the isotropy groups. So for each unit, there's a CPC map from the reduced groupoid C-star algebra into a group C-star algebra around the isotropy. So it's not necessarily the reduced. E is potentially exotic norm. Um, but these maps are induced by restriction of curly C elements to their values on the isotropy. E here is actually it's sort of like a quotient norm. If you give curly C here the reduced norm, then at the level of these dense subalgebras, you could induce a norm on the group ring here just via the quotient norm and then take a completion. So, and these family of CPC maps have the nice property that they detect when a positive element is zero. So if you have a positive element and under all these restriction maps, it's zero, then that element has to be zero. And the consequence here is that since ideals contain positive elements, right? The singular ideal is zero if and only if all of its images in these under these restriction maps are zero. So we'll denote the image by J lower U. And these are called the isotropy fibers of the ideal. And these are in general for ideals and reduced groupoid C-star algebras. These were studied by Christensen and Neshviev in 2022. And they're shown to be ideals in the group C-star algebras with these norms E. So the strategy is actually to calculate what these isotropy fibers are by utilizing the Hausdorff cover groupoid and some facts about a special class of CPC maps, which I call compressible maps. And I think the Hausdorff cover groupoid's been talked about in this seminar before. So I'm not going to mention this part of the proof so much. I'm going to focus on sort of my contribution, which is identifying this special class of CPC maps. So these compressible maps they behave quite a bit like star homomorphisms. The definition is, so let eta be a linear map between C-star algebras A and B, and C a C-star subalgebra for which the restriction of eta is a star homomorphism. Then we say that eta is compressible to this star homomorphism if for every element in A and epsilon, there's a C inside of the subalgebra as well as a phi in the unitization of the subalgebra, such that eta C is equal to eta A. Eta sends phi to 1, and the compression of A by phi is within epsilon of C. Okay. So that's the definition. It's sort of like the if you sort of draw a commutative diagram, you can sort of go from A to C by compressing. Sorry, my alarm is going off. Yeah, you can go from A to C by compressing, and then you can go from C to B by applying eta, and sort of the diagram commutes. You could you could similarly go from A to B just by applying the definition. But this only commutes approximately, right? Because we have this epsilon. Um, and yeah, so what I show in my paper is that these maps behave, they have a lot of shared properties between star homomorphisms. So compressibility implies CPC. So they're all completely contracting and completely positive. They send ideals in the C-star algebra to ideals in the image. And the property of compressibility is preserved under matrix amplifications and quotients, as well as norms of elements under compressible maps satisfy an excision property. So if you depends if you're familiar or not with the excision property for the norm of an element under a star homomorphism. If not, then you don't bother with this, but it's if you do know it, then this a similar property holds for compressible maps. And then the main thing that I need about compressible maps to calculate these isotropy fibers is the following theorem. So suppose you have a commutative diagram of C-star algebras where I and J are star homomorphisms, so the horizontal maps, and eta 1, eta 2 are compressible to star homomorphisms from C1 and similarly from C2 with eta 1 surjective. And furthermore, assume that there's an approximate unit for the kernel of the compression of the first map here, such that after applying I, you get an approximate unit for the kernel of the compression of the second map. Then you can actually show that the image of the kernel of I, which is an ideal, under the map eta 1 is equal to the image of is equal to the kernel of J. So essentially you have a commuting diagram. The vertical maps are compressible, and the property is that both of the compressions share an approximate unit when you apply the star homomorphism I. And the conclusion is that you can map the kernel of I to the kernel of J using eta 1. So this is very useful, and I'll get back to it. But I want to describe a very large collection of these compressible maps. And we'll do this on groupoid C-star algebras because that's what we're interested in this talk. So first, define a subset of the unit space of a groupoid to be locally invariant if whenever the groupoid element if whenever you have a groupoid element G which satisfies the property that the range and source are inside of X, then there's an open set U containing that groupoid element such that for all other groupoid elements in that open set, the range of any element being inside X is equivalent to the source of that element being inside of X. So if you just restrict your attention to an open set around G, then it looks like your groupoid is actually invariant. Or it looks like the subset X is actually invariant. And there's lots of examples. Actually, any finite set of units is locally invariant. And the Hausdorff cover has a nice property that if you have a locally invariant set in your groupoid, then its lift to the cover will also be locally invariant in the cover. And the theorem is that given an Natal groupoid and X a closed and locally invariant set, firstly, the reduction of the groupoid to X is going to be a tau. Secondly, the restriction map from the reduced groupoid C-star algebra to C-star algebra um, of the reduction by X is compressible to a star homomorphism from uh, this groupoid H here. And H is an open subgroupoid which has the same unit space as G, has the same reduction as G to X, with the extra property that X is actually H invariant. Um, so like you can actually reduce your groupoid to a open subgroupoid for which X is actually H invariant. And the theorem says that the restriction map from G to X is compressible to a star homomorphism, which is just the restriction map from H to the reduction of G to X. So that means that all these nice properties about compressible maps are satisfied for these restriction maps. So the reason why I mention all this about compressible maps is that actually does the calculation for us to calculating the isotropy fibers. So I would just want to mention that, yeah, so if you have a unit, like I said, it's going the singleton associated to that unit is always a locally invariant set. And that collection of subgroups I defined before turns out it's actually a subset of the unit space of the so-called essential Hausdorff cover. And it's a closed subset as well as being a locally invariant set for this cover. And we have this sort of commuting diagram where the vertical maps are these restrictions which are compressible, restriction to U and restriction to curly X at U. And down below is just the reduction identified. It's turns out it's like the groupoid associated to all the cosets of these subgroups. But anyways, this top map here, Q, has a nice property that its kernel is the singular ideal. This was shown by us in earlier this year. And then in my paper, I calculate this kernel of QU, and when the isotropy is amenable, it's actually the kernel of the direct sum of all these quasi-regular representations. And that's how the characterization gets linked back to what we're doing here. And this commutative diagram actually satisfies the hypothesis of theorem D using, so yeah, so we have sort of automatically that the image of the kernel of Q under this restriction map is equal to the kernel of QU. And that's just saying that the image of the singular ideal under the restriction map is identified with this kernel here. Yeah, so that's how compressibility helps us. It after proving this commutative diagram theorem, it sort of just follows out by yeah. So any questions or? Um, yeah, so since every finite set in the groupoid is locally invariant, it's kind of interesting. Like these compressible maps behave a lot like star homomorphisms. So you can kind of think of these of Étale groupoids as sort of generalizations of residually. So they're sort of like residually discrete groupoids because for every finite set of the unit space, you can go from your groupoid, reduce it to that finite set and get a discrete groupoid. And as the finite set gets larger, you're sort of getting a better and better approximation of your groupoid C-star algebra. And these restriction maps behave a lot like star homomorphisms. So in a sense, groupoid C-star algebras for Étale groupoids are residually discrete groupoids. Okay, and sort of following that, the philosophy that you can reduce problems about the singular ideal to problems about the isotropy. I have this following characterization for when the singular ideal intersect the convolution algebra we defined is zero. I should mention that earlier this year, me and my co-authors characterized when this is zero in a different way, which included the topology as well as some algebraic property. But here, this is an entirely algebraic property. So the singular ideal intersect curly C is zero if and only if for every unit, the following system of linear equations has no non-zero finitely supported integer solution. So here, these AGs as a variable for each groupoid element, for each group element in the isotropy. It takes on integer values, and the summation here is over a coset of a subgroup in this collection of subgroups curly X of U. And the characterization is that for every unit, this collection of linear equations has no non-zero finitely supported integer solution. So finitely supported just means only finitely many of these AGs are non-zero. So if you look at characterizations of when the Steinberg algebra, if you know what that is, of a groupoid, its singular ideal vanishes. A lot of them are in terms of well, you got to check if a certain set of equations has no solution, and so this is sort of this is the reason why you have that sort of characterization in the examples of Steinberg algebras for which the singular ideal has been studied before. So given that there's this nice characterization when the singular ideal intersect this convolution algebra is zero, you can ask the question of whether does that being zero actually imply that the singular ideal is zero? Because if it did, then you would have a really nice algebraic characterization for when the singular ideal vanishes. Um, and so I study this question a bit in my paper, and I show it's equivalent to a property about group C-star algebras. So we'll say a discrete group gamma has property I if for every collection of subgroups curly X of gamma, such that the kernel of the direct sum of all the quasi-regular representations associated to those subgroups inside the group ring is zero. If that property holds, then the kernel inside this C-star algebra completion of the group ring is zero. So it's sort of like whether you can detect if these certain ideals are zero based on the group ring. So that's property I. And I show that question A, the problem about the singular ideal, has a positive answer if and only if every discrete group satisfies property I. So that's sort of like a meta theorem. And it tells you that to solve this problem for groupoids, you have to solve this problem about groups. And moreover, question A holds true for groupoids with isotropy groups that satisfy property I. So, and by establishing a bunch of permanence properties for property I groups, I show in my paper that property I holds for groups that are direct limits of virtually torsion-free solvable groups. And that class, that includes direct limits of groups of polynomial growth, as well as linear groups that are immutable. So matrix groups that are immutable. And I think that's all I wanted to discuss. So thanks for listening.
Thank you, Jeremy, for the talk. Is there any question for Jeremy? Let's see. Okay, if not, I will stop now the recording.